This is where we do the intro music. This is the
Oh yeah. You
it's
said you had been working on a rap that you wanted to try out.
I told you that in confidence. It's a very vulnerable moment. So if I were going to
um,
rap anything, it would be this Gen Z Bible that I think. Did you see this thing that
oh, that I loved it. I was gonna try to like mix in some Gen Zism, but like I would just flub it. So, but it was delightful.
So the question is, so my kids told me that like, Dad, you think this is way too funny? I'm like, I do think this is really funny. This is really funny. I thought there were some great lines in there. I should, if folks did not see this, did you have a favorite verse in there, Adam?
I think there was like a "We got you, fam" kind of thing from the Snake that really had me going.
I did like it when Adam said and said, "What is up, my mammals? Go forth and vibe in this Minecraft paradise."
Go forth and vibe.
There's so much good stuff in here.
Yeah.
And then the divine G caught them in 4K and said, "Bruh." that also did send me.
I you know what, I didn't tell my own my son because like I also found it way too amusing, and I think he would have been really off put by how funny I thought it was.
Yes, well, you picked wisely. I did not pick wisely, and I just thought it was way too funny, and really insisted on reading way too many verses aloud to my own children. So I just
Where did this book come from?
our colleague Aaron, Aaron.
Oh, nice.
I guess his maybe brother showed him this. I've got no idea. I don't know where this mythical thing came from, and a bunch of other people were like, "Show me the rest." I'm like, "That's all I've got. All I've got is one page. I don't know." It's really amazing. It was a bit of a debate in this house, in our house, about who wrote it, what generation wrote it, and my kids in
Hmm.
particular believe that like no self-respecting Zoomer wrote this. This is not Gen Z. This has got. This is where do you my kids troll me by calling me a boomer, and it really does successfully troll me. I'm really angry about how successfully trolled I get every single time. They're like,
I
one
mean,
of
the
you boomers,
AARP is kind of nipping at your heels these days, anyway. So
ARP is nipping at my heels. He's like, one of you boomers wrote it. I'm like, I'm room. Anyway, sorry. Uh, Compile times. Welcome. We got Rain here, Rain Paharia, and Sean Klein and Steve Klabnik to talk a hot topic, compile times. Adam, I thought we may give just an intro to this about our personal journey through compile times, because and maybe this is like part of the problem is that you and I have our expectations set too low. From do you agree with me that we've got
no, dovetailing perfectly from the generational conversation. No, I agree. I mean, it is. I think it bears explanation that my first job, your first job, was at Sun Microsystems working on the Solaris kernel, and the script to build the thing is called Nightly,
nightly?
which tells you the frequency at which it is expected to complete.
And at one particular dark moment in Sun's history, it took more than 24 hours to compile. Compile
Jeez.
absolutely everything. Yeah, on this is considered to be a low point in many different dimensions in terms of like because there's a little bit of like your ratio of like system complexity to system performance is clearly you overburden the system when it takes more than so yeah. I mean that was kind of our coming. It was we're just you get used to very certainly to build everything just takes a long time, and you also just get really used to doing a lot and kind of like pencil and paper. But that's really not the way. I mean, there's a bunch of other software we developed where we love those quick iterations, and the quick iteration becomes really important. And so I confess that when like I kind of liked, I mean, liked is a bit too strong, but the fact that Rust did take a long time to compile, I just felt like it's like the computer's doing work. It's taking a long time to compile because it's solving really hard problems for me. And I kind of thought it was great. This is really
Yeah.
pathetic. It's like
No,
stock times.
no, absolutely, but it also kind of sneaks up on you because for at least most of the things. I mean, everything I've worked on at Oxide, it didn't start off slow. It got slow, and
That's slow.
you're in the pot of water that's gradually heating up, and it's hard to notice that you're cooking.
Yeah, and I gotta tell you, the first time I really got burned by compile times, so Humility, the debugger for Hubris, was taking longer and longer and longer to compile. And that is one of those things where it's like, I'm just trying to change the output of something. Like, I really,
Mm.
like, that thing needs to be one column over to the right. Like, I really do want to, like, okay, come on, like, let's see what does it look like now? What does it look like now? What does it look like now? You really want to do these quick iterations. And one of the problems there is like anytime you touched anything the way it had been kind of architected up to that point, it had to rebuild everything. And sometimes I feel like it's great to have new employees join a company because you feel like you need to get things cleaned up because you're embarrassed. And I'm not sure if
Yeah,
you get
yeah.
those
Company is coming for dinner. It's like
companies
tidy
coming
the
for dinner.
place up.
Companies
Right.
coming for dinner, and I gotta like God, like let's act like it was. And so I feel like Matt Keeter was about to join Oxide. I'm like, he can't join with these kind of compile times. Like this is no good. I gotta scramble to make this thing so you can actually. And so I can't remember if I'm right now, Matt, wherever he is thinking like, this is the compile times after you work on it. Like
That
that's
was
just
better.
sad.
Like that.
Yeah,
Whoa.
exactly. It's like I feel bad for you. But yeah, it used to be a lot worse because and then we made it better. But I think you're right. Like it kind of incrementally gets bad, and then you kind of wake up and you're like, wow, these iterations are taking a long time. And then I think there's also a tension with just the size of the repository, right? And we have tended towards not quite a monorepo, but we've got the Omicron, our control plane, is a single repository. It's big. Um, so there's a lot of compile work that happens. And Sean, I don't know. I mean, you've been kind of with Omicron from its very earliest days. So you've kind of felt this thing get. And I know this is an issue that has definitely been under your fingernails and spent a lot of time investigating. Do you kind of want to talk about your history with respect to Omicron build times?
Yeah, the fact that it is a monorepo is definitely one aspect of it. I definitely agree with the like boiling frog in water sort of analogy that was being made here, just because as we were building it up, I mean, build up a small prototype of a control plane that does a few interactions with a database and that exposes an HTTP interface, like it's not so bad. But then you start to grow it, you add authentication systems, you expand kind of feature set you have, as well as how big the interface is that you're exposing and how you're communicating between a lot of different services. Like it just gets, not only do the build times grow, but it's a lot harder to see and to make it clear which changes are making things worse and where things are slowing down. So um, I don't know, it sort of became a problem of like, especially getting kind of crossing a certain threshold of not only improving the build speed was a big factor, but also making sure that we could actually interrogate the build and figure out what different aspects of it are causing it to be slower or faster, or like what are the different ways that we are building it. Because building the building the entire control plane under test is very different for building the entire control plane under getting ready for production versus building it. If sometimes the developers use cargo check commands, which don't actually produce artifacts, but they can still do type checking and give you a lot of quick feedback. And like each one of these different flavors and different ways to build has kind of different settings and different parameters. And that's something that Rain actually kind of uncovered pretty recently. That was a big winning point. It was unifying a lot of that stuff. But yeah, that sort of aspect of being able to kind of ask the system, why are you taking so long, is one of the most important parts of all of this for getting to the bottom of what's going on.
Totally. Yeah, and also, but just kind of before we get to some of our methodology there, because I think the absolute times do actually matter, right? Because it feels like once you hit a certain threshold of like, I'm not going to sit there and stare at this thing, and I don't know like what that threshold is probably different for different people, but somewhere I don't know, somewhere in like the 45 seconds to 3 minutes, where you're like, okay, I need to like go off and do something else. And then it's like actually the build time is not 3 minutes. It's actually like 38 minutes because you got distracted by something or you're off on, if you're lucky, you're off like helping out a colleague or engaged in another productive discussion. I think if you're many of us, you're more likely like, how long was I on that Hacker News thread or what have you? And it's like, yeah, because I left because of the build. It's kind of like, you know what I mean? It's like, it feels like there's I found that I got much more productive when I set timers for some of the longer things that we need to go do. And my timer would go off. Like, oh, okay, wait a minute. My build needs to come out of the oven now. So, I mean, because Sean, the absolute times do matter, don't you think?
I totally agreed. And this is actually, it's a good point of like, there's many different types of builds. Like, are you checking out the repo for the first time and doing a build from scratch? Or did you edit one file and you want to see what's going on? Because your comment earlier about like, coming to Rust and feeling like it's doing things, right? It's thinking about the build, it's doing borrow checking, it's doing all this fancy stuff that benefits me as a developer. Um, I can empathize with that the first time that you build it. But when you change one file and it's cranking along for as you said, changing a small output or changing something that doesn't feel like it should take that long to build, it becomes a lot more frustrating. And there's kind of that question of like, why? What's going on?
Yeah. So Steve, to give us some history here before we get to Rain's big win, the it used to be, I think, like actually shortly before I came to Rust, there was no incremental compilation whatsoever, right? I mean, wasn't there a time when everything had to be rebuilt all of the time?
Yes. And that's like, to be clear, that's like each crate would need to be rebuilt individually. So like you weren't in that world, you weren't like recompiling all of your dependencies every cargo build. It's just that like this is actually kind of an interesting thing where we have historically used some terminology that's like kind of wrong now because of this. Because it used to be like, what is a crate? A crate is a compilation unit because it's a thing you pass to Rust C. But like that's not true anymore because then we added incremental compilation and now compilation units could be much smaller. So like all that stuff got tacked on kind of later and makes things a little fuzzy. But yeah, like it used to be even worse. Right.
Well, I think as I gather with like a lot of things, I mean, I showed up to Rust in 2018 and I feel like a lot of things had just gotten suddenly better, or maybe just I've got like no self-respect and a high threshold for pain, because a lot of things that I think had been pain points were being very quickly alleviated. And
it's not on the issue of compile times, but like this has been one of my recurring drums throughout like the description of early Rust history, like that I beat on all the time, which is like a lot of the Rubyists who came to Rust in the early days, our function was to tell the systems people, you can in fact have nice things. It is in fact possible, right? Like this is kind of the story of cargo in general.
Wow,
like people were skeptical. Well, this is the second cargo because there was like 5 different build systems way back then, but this is not about those things right now. But the point is like some people would be like, yeah, I'm never going to use that cargo thing because it's a toy and it can't do real systems programming. And then cargo got shipped and they were like, oh my God, I'm never writing a make file again. Their sun comes out, the birds start singing, so yeah.
It is funny you say that because I do feel like I'd be like, no, we don't deserve nice things. No, long build. No, we don't deserve it. We've never had it. It's like, no, you can actually have nice things. Actually, and then when you do have nice things, other great things become possible. And Adam, do you use Rust Analyzer? You do, right? No.
Yeah. Oh, yeah. I mean, wait, are you turning the tables on me? Like I feel like I've spent the last year and a half trying to convince you to use it.
No, I was pretty sure I was trying to convince you to use it, wasn't I?
What is going on?
This is actually
just some new level of gaslighting. No, I use Rust Analyzer. Like I don't like looking at code reviews on GitHub because I lack the annotations that Rust Analyzer gives me in the editor.
Yeah, and I need to. That's clearly like amazing, Rust Analyzer, and
it is amazing.
Should I use Rust Analyzer before or after syntax highlighting? If you had to like stack rank them.
Oh, Rust Analyzer over syntax highlighting all day. It's way more useful.
Yeah, no, it seems like it'd be very valuable.
There was a possible future where Rust Analyzer would slowly have eaten the compiler, and then at some point that dream died. But I still alternate history Rusts. I kind of wish that plan had gone through.
So elaborate on that, Steve. What does that mean? That means that there is that Rust Analyzer. Yeah.
So compiler technology has changed a lot since the Dragon Book. And so the way that we like teach people how compilers work and the way that a lot of people like think about compilers is like, okay, you lex, you parse, you have some sort of AST, you do transformations of the AST, you do code gen, you spit it out. But like the thing is that only works for batch compiling. And the history of especially tooling is that one, you need to really deal with the incremental case because we are now, like running the equivalent of a compiler all the time. And secondly, that like you need to handle malformed input better than a compiler. Like a classic batch AOT compiler, My friend Tef has this post. He's like, programmers like to read blog posts like they do a compiler would read code. They find the first sentence they disagree with and then bail out and like print an error message. And that's like how classic, batch compilers work, right? Is like, here's my error. And maybe they give you some additional ones, but often they're not that great. And then they go back. But like things like IDE tooling, like it would be really bad experience if you had a typo in your source code and all of the inferred types disappeared from your UI because Rust Analyzer could no longer figure any of that out, right? So we kind of have these like two different things like coming onto compilers. And so specifically the like Roslyn compiler for C#, which eventually kind of ate the classic compiler and replaced it, is based on incrementalism upfront. And so the Rust compiler was written as a very classic batch compiler originally. And now it is a much more complicated amalgamation of kind of sort of both of them. I am not as knowledgeable about the compiler internals as I used to be, so I don't want to make too many sweeping statements and say things that are not entirely true. So please take what I say with a grain of salt. But the point is they added this thing called the query system that's like intended to make it more incremental and like better at those kinds of things. But you could also make the argument that like this doesn't work well unless you start the project that way from the beginning, because the techniques that you use to implement all these things work differently based on the like you're changing the fundamental architecture of the system. It is just a different system. You know what I mean? So yeah.
Interesting. Yeah, and so you kind of mentioned like the ability to. So meanwhile, stuck in the kind of the batch compilation, we really need to have the understanding of where all of the time is going. So I guess maybe Sean, do you want to talk about like some of your explorations, like I said, as a segue into Rain here, about where is all the time going? So I running cargo build, and that last step in particular seems to take a long time. What's happening there, and what's some of the tooling that you've used to figure out what's happening?
Yeah, so like the first tool that I'd recommend, if anyone else is building a Rust project and is kind of in this similar position, Cargo Build has a flag that is -- timings that's pretty good and it's pretty well documented. And it can basically give you a build graph, like breakdown crate by crate. Where are things being built kind of on a linear timeline? And you can see that output. And that's pretty useful if you're looking at kind of like which one of my crates are taking the longest time to build. That can be particularly useful if you have like, I have a dependency that takes a really long time to build in my small Rust project and it just inflated a lot, or I'm building a bunch of stuff in a workspace, but I'm trying to figure out which one of these crates is the one that's actually the long tail. But that sort of stops at a certain granularity. You really get which crate is it, and then you kind of stop getting answers at that point. Okay, I can see this crate that takes a long time to build, and I'm working on it, and so it makes sense that it's rebuilding. But then, like, why that one? What is actually going on under the hood here?
Right.
And this is where I find the space of like optimizing Rust builds really interesting, because there's not really one answer for where you go next. There's a lot of different answers. There are a lot of
always a special kind of challenge, right? When there's a lot of different answers, because people will get a lot of suggestions of I think the problem is over here, or the problem is over there. It's like, well, you're actually all kind of right to a certain degree. But it gives you, I mean, it's great to have a target-rich environment, but it makes it complicated.
Yeah, for sure. There are a lot of different like signals that you can look at, but a lot of them are like just that, like they are signals, they're proxies for other data. So like a classic one is you can look at tools like Cargo LLVM lines or Cargo bloat. Like those are great ways of saying like, hey, what are the aspects of my build that are contributing to a large binary size? But that's kind of that sometimes helps. That sometimes helps for finding the spot where your build was actually slower, but it's a proxy, right? Like you're saying, right. The things that are really big, like that can help, and that has helped us in several cases where we used generics in a way that inflated what the compiler was actually working on, and like those tools helped find those cases.
And then how did you solve that problem when you have like, okay, so we're getting more, I mean, more monomorphization than we want. How do we actually go address that, or how addressable is that?
Yeah, and so there are a lot of different people who have written about this. And Steve, I know you personally worked through this on our Dropshot, our HTTP server. But the kind of classic way of doing this is if you still want to have the same function signatures, like let's suppose that you have a function that's generic and it's fully generic, generic parameters, whatever the body of the function is, it's just that body. Every single time you call that thing with new generic parameters, you're going to be creating basically a new copy of that function. I'm hand wavy because the compiler does different things than that, but that's a rough proxy for how to view it. A really common tool here is you create a very thin shim you have a generic version of that function that calls to a not generic function. So your generic call basically becomes a very, very thin call to a not generic function, which means that like you do have a bunch of copies of this generic function, but it's much, much, much smaller. It's just taking your arguments and making a function call with it. Sometimes that's possible, and sometimes that's not possible, or it's very, very painful to refactor code to be able to do that.
And have you found that and presumably a small fraction of these give you the biggest possible wins? I would assume it would be, I mean, did you find that you can get big wins doing this?
In certain cases, I hate to do this because it's like, yeah, go for it, Steve.
I was going to say, I linked the PR that Sean was referencing a minute ago in the chat. It is a -4 plus like 8-line PR, 10-line PR that resulted in like 5 seconds being knocked off the build times of Omicron. So occasionally you get great, pretty significant leverage. Of course, this is always subject to things. This is based off of an optimization called outlining that compilers do. You're basically doing the compiler's job for it deliberately. And so sometimes, like all optimizations, it's better and sometimes it's worse.
Yeah, going through this experience has like changed my mind with respect to generics before fighting compile times. I was so excited about generics and Rust for the ability to have like good expressibility of different types. Being able to really have unique types that represent different things and fully exploring that part of the type system. But after going through this aspect of build times, I still appreciate that, but it's definitely with a very, very solid grain of salt.
Interesting.
Where these things have a cost. And in the case that Steve linked, I think that's actually a great example of where it worked best, right? Because that's a case where we basically had each one of these endpoints that was a generic thing, and the body of it could be separated out. But depending on how you're passing around generic parameters, it's not always possible to make these refactors. Like, Steve, I remember you and I worked together on trying to change the generic parameters of one of our crates, and we just couldn't detangle the level of generics that was happening there. Because it wasn't as simple as like the body could be made not generic, and the signature was like it just there were generics that were being passed through for very legitimate reasons. Sort of as in many ways also made me more comfortable with the idea of using very judiciously trait objects where it's appropriate.
I also need to confess briefly that part of the attitude that Sean is expressing is like kind of my fault, because I basically like put in the book and told everybody and was part of that early culture of like always use generics and not trait objects, always use generic and not trait objects. And we didn't like do as good of a job of describing the balance. I still think that ultimately that's like the right call, but I think that many people don't fully appreciate the trade-off, partially because of like history, and I didn't do a good job of explaining it. So
yeah, it sounds like are you going to have a tell-all retrospective where this is going to be
God.
like...
I will tell some things as a retrospective all the time, but of course not every story gets told.
Right. You need do a documentary where you can confess it all. Expand a little bit on before Steve goes full Robert McNamara on us. Could you expand a little bit, Steve, Sean, on what you mean by the trait objects and where you use that now instead of generics?
Right. So if you're acting on a object in Rust, where you really care that object implements a trait or a set of traits, you basically have more or less two choices with how you're going to interact with that object. Let's suppose that you're writing a function that's going to take this thing in. You can make that function generic and operate on a generic impl t version of that trait, Or you can make that function not generic, but it can act on a DIN version of that trait. So that can be like a reference to a DIN object. If you're doing more complex things with a lifetime, you might need to box that object to make sure that you can actually pass it around. But that's more or less the trade-off that I'm discussing here is like, which one of these do you want to take? Do you want to do the DIN object or do you want to act on the generic? And if you're acting on the generic object, then the compiler can successfully basically take the template that you've provided to it and paste in the appropriate type as efficiently as possible at compile time. Whereas if you go the DIN route, you are adding a layer of indirection that at runtime will cause an extra lookup, more or less, that's happening, and it will cause Rust uses fat pointers in this situation, so it's going to keep around. I believe the terminology here is it still is called a vtable in Rust, right? Or I don't know if there's a different term for it.
Yep.
Yeah.
The main significant difference is between the way in which the code is laid out in C++ and in Rust, but it's still a vtable and it's still called a vtable in both languages.
Yeah. And so depending on what your situation is, like if you're writing high performance code, this can make a difference. I would also throw out that in many situations, if you're doing this in code that is also opening a file, communicating over a network, anything like that, the cost of whatever you're doing, the choice between the template and the trait object is going to be so low and so negligible compared to the other work that's ongoing, that it probably won't make that much of a difference. But there is that trade-off to be made, right? And there's always that kind of desire to reach for, well, you don't want to set yourself up for something that's harder to optimize later, but it's sort of that question of, are you optimizing your runtime or are you optimizing your build time? And that classic, at the end of the day, it's kind of speculative until you actually look, because who knows? Maybe by having generics, if your binary size is bigger, you're actually blowing out a cache size. So, but that is sort of the trade-off between which one of these you're paying for, the generic route or the trait object route.
Yeah, the dog is big on generics, and it's just trying to be like, don't even mention traits. Why are we talking about traits here? The runtime cost. Mention the runtime cost. But I also feel, and Sean, to your point about it, in most cases, the actual runtime performance difference will be negligible. I do think it's really important that one be quantitative about all of this stuff, because some of the things that you think are expensive are not as expensive as you might think, and there are some very things that are really very costly elsewhere, which we will. And Sean, one of the things that you said early on is that one of the things that's most frustrating is when you, the programmer, really feel like Rust is doing work it doesn't need to go do, and I feel like that happens most frequently when you do a build, you make a small change. You do another build, it's like, why are we rebuilding that now? Like, we now seem to be rebuilding a bunch of stuff. And Rain, you had one of these very recently that maybe you can go into depth on, where you got a lot of stuff being rebuilt that you felt should not have been being rebuilt. Can you go into a little bit about what that problem was and how you debugged it?
Yeah. So I just I want to start off by saying that I love Cargo. I think Cargo is fantastic, right?
Cargo is moving uncomfortably in its seat. Like, what's happening? What's coming next?
So Cargo has a lot of really, really useful features for all sorts of open source scenarios. Like, for example, like it lets you turn individual bits of a particular crate on or off. It lets you cross compile. It lets you do like many other things that are actually kind of fancy. The thing though is that a lot of those features end up actually being pretty pessimal for compile times, and at this point I've spent like probably over a year of my like dev time trying to figure out, okay, how do we make this better? And so both at my last role at Meta as well as over here, I have spent a long time analyzing, okay, so a common situation is that you're in a large workspace or monorepo or whatever you want to call it, and you run cargo build, right? And then something fails, right? Let's say something fails, and then you go and run, and then you want to rebuild a particular project, so you run, or particular crate, so you run cargo build -p with the name of the crate. And all of a sudden, you're not just rebuilding that crate, you're actually rebuilding the entire world. And the reason that happens is because of the way Cargo works, and specifically Cargo's feature works. The way Cargo's feature works is that you specify like a set of crates or a single crate or whatever to build, and it looks at all of the dependencies, and what it does is that, let's say that you have two dependencies, A and B, and there's a transitive dependency, C, right? Now, let's say that A depends on C with a particular feature foo, and B depends on C with a particular feature bar, right? Now, what happens is that if you build A and B together, then Cargo will unify those features such that C is built with the features foo and bar. But if you build just A separately, then then you just build C with foo, and if you build B separately, then you build C with bar. So if you do these three builds, you're actually going to build C 3 times. Now, that doesn't sound too bad at first, right? But what happens is that if a crate is rebuilt, then all of its dependents are also rebuilt transitively. So as a simple example, the syn crate, which is widely used in the Rust ecosystem for syntax parsing, basically every proc macro uses it. It has like 15 or so features, right? And I don't know the exact number, but it's something like that, right? And a lot of crates that depend on syn actually enable some subset or the other of those 15. So, it's like some proc macros need the ability to visit the Rust tree. Some proc macros need like the ability to like serialize and so on, right? So now what happens is that you have this essentially 2 to the 15, I think, feature sets that could potentially be built. And so all of a sudden you have this like literally combinatorial explosion of feature sets that can be built. And because syn is so core, every single thing that depends on syn also gets rebuilt. So all your proc macros get rebuilt, which means that all your proc macros get run again. So anything that imports those or uses those proc macros gets rebuilt, and so on. It's honestly like, it is kind of a disastrous scenario at the moment. Like this is like not good at all. And so that's the world that kind of when I started looking at the problem, I saw. And so I've built out a whole bunch of tooling, which I can go in more detail about, like, trying to fix this problem and so on. And it turns out that, it does work. It fixes the problems, though it ended up actually exposing a whole bunch of other problems that we found out while trying to figure out what was going on.
Yeah, right. So if you could describe the tooling just in a little bit of detail so people can know where, boy, I've got this problem. Like how do I alleviate this? Because it feels difficult. It feels difficult to alleviate.
Yeah. So, all right. So, several years ago, so I used to, a long time ago, I used to work on Firefox. And so I got pretty intimately familiar with the Mozilla Central repository. And, even after I stopped working, I'd still like check it out, browse the source code every so often. And so when they introduced Rust, a thing that I noticed pretty quickly is that they ran into the exact same issue. And so they introduced what they called a workspace hack crate. And the idea behind the workspace hack crate is that it is this crate that is sitting on the side. It is completely useless, except that for certain dependencies, like, for example, syn, it actually specifies the union of all possible features that all of the dependencies that use syn actually end up requiring. So and also every single crate in the workspace in Mozilla Central actually depends on this workspace hack crate. And so this solves the problem to the extent that, and this is managed by hand in Mozilla Central, as far as I know. And so this solves the problem to the extent that, there's like a human that is like keeping things up to date, because everything depends on workspace hacks. So syn always gets built with the same features. So I ended up writing a bunch of tooling to actually automate this. Cargo Hakari. So this is an automated workspace hack manager that I built out, and what it does is it basically looks at all of the dependencies and figures out, okay, here are all of the dependencies outside the workspace that are built in more than one way. And then it just adds lines to the workspace, to the creates cargo.toml saying, okay, build this with the union of all features. So it's something that gets automatically managed. It's built to also be used in CI to make sure things are kept up to date and so on. And so I switched Omicron over to that a few months ago. Omicron being our control plane monorepo, and so the results of that were pretty good. Like now, if you did jump around and did cargo build -b foo, cargo build -b bar, and that did improve build times quite massively. There ended up being a whole bunch more that we needed to do to achieve that, but that was kind of the big thrust of what we achieved.
Yeah, and that's great, Rain. Just because one of the pathologies we were seeing in that Omicron repo is there's some kinds of work that people kind of didn't want to do, like stuff that should be easy but wasn't, because even doing those narrow kinds of builds took so long. So in taking some of those rapid iterations, Brian, that you were alluding to, just weren't rapid. So it's been a big boon.
Yeah, and then it's been a big boon and a lot of, but then Rain, we had an issue where you've done all this great work with Cargo Akari, and then we're still rebuilding stuff. You're like, wait a minute, I fixed this.
Yeah, so
I feel it's like I've had that feeling a couple times in my career. It's like, how is this? You are not allowed to be a problem right now because I've already fixed you. So sorry, problem. Did you not get the memo? You've been fixed. What are you doing still here?
Right. So that's that. Coworker filed an issue on me saying, I was expecting Cargo Hakari to fix this, and yet it seems better, but it isn't actually completely fixed. So to actually diagnose that, I ended up doing a whole bunch of debugging. The tool I ended up using the most is Cargo actually has this thing called a unit graph as an unstable feature. So what you can do with unit graph is, all right, so backing up, right? The way build systems work is that you have what is called a dependency graph, right? So you write out a workspace which has these cargo.toml files. These cargo.toml files specify, your dependencies and so on. And then what Cargo does as its build system is that it turns this dependency graph into a more fine-grained graph. And that fine-grained graph is what is called a unit graph, or there are other build systems like Buck have this notion as well, and they call that an action graph. So it's basically the same thing. What that ends up doing is that it expresses each step in the build process as an individual atomic step. So for example, let's say you are building a crate that has a build script, right? So the first step for that needs to be compile the build script. The second step is run the build script. And then the third step is compile the actual crate, right? So a single dependency turns into 3 nodes in this unit graph or action graph. So how do you examine this graph? Because this graph actually seems pretty useful, because this will actually tell us which dependencies get rebuilt or why dependencies are getting rebuilt. This graph captures things like, like what settings are used, how builds are done, the features that are enabled, and so on. So Cargo does let you spit out a unit graph using this -- unit graph option. So I ended up basically examining this unit graph by hand and discovered a whole bunch of things that were preventing objects from being reused again. So one example of a thing that was preventing objects from being reused again is that when we build Omicron, we build it and we ship it with panic equals a BART set. So I'll go in a little background there. By default, you have a Rust program, you panic, and what happens is that you get this backtrace. You can actually catch this panic. Typically, it isn't meant as an exception handling mechanism, but in some situations you can use it as an exception handling mechanism. And that is what is called panic equals unwind. Now, when we ship Omicron, we actually ship it with a different panic setting, which is panic equals abort. And what that does is that it actually aborts the build rather than simply unwinding it, or aborts the process completely, right? So you get a core dump, which is useful, but otherwise the entire process dies, and something must bring it up again if it's like a service or something. So we had set panic equals abort for both release and dev builds, but it turned out that if you're doing a dev build and that dev build has a proc macro or a build script, then that is always built with panic equals unwind. And the reason that is built with panic equals unwind is that a proc macro is an in-process plugin for the Rust compiler. So if a proc macro is built with panic equals abort and the proc macro panics for whatever reason, then Rust C would not exist anymore, so it would not be able to provide a useful error message at all.
Yeah,
Yeah.
Rain, we kind of kicked off talking about the Gen Z Book of Genesis, and I really feel like this is where I felt like we all collectively bit the apple on this one, where we've got proc macros are amazing, but of course, because you get to write software that becomes a part of the build process, but there is a cost to that, and of course, like when you explained it, I'm like, oh yeah, of course that makes sense. You would not want to have panic equals abort, because then it would be bad. Basically, a bug in a proc macro, a panic in a proc macro that you actually want to bail out and have an error message would result in just like a seg fault. And
exactly,
it's not really the experience that anyone really wants, especially when you're trying to debug your proc macro. You should be and it's on the one hand, it's like, God, I wish it were different, but I can see why it's the way it is, and it's tough. And Rain, can I ask, like, is that just something you kind of knew, or how were you able to make the leap from like, wait a minute, I know that there's a different a different panic setting for proc macros?
So this was not something I knew before doing this investigation. So I started doing this investigation, and I'm like, okay, it looked like there were like 7 copies of Surdy.json being built. And I'm like, why are there 7 copies of Surdy.json being built? So I started looking at all the individual copies and seeing what they said. And so in some cases, it said that those copies were built with unwind, and in other cases, it said that those copies were built with abort. So I started scratching my head, and I'm like, and I looked at our workspace cargo.toml, which specifies these settings, and it just said panic equals unwind for dev builds. Sorry, panic equals abort for dev builds. So I started looking at it, and I'm like, okay, this is something weird that Cargo is doing. And then I literally went to github.com/rustlang/cargo, and in the search box up top, I typed in unwind. And people like hate on GitHub code search these days. I mean, I thought like the first result it provided was exactly relevant. Like it showed me that, okay, there is actually a line in Cargo which forces panic equals unwind for proc macros and build scripts for this exact reason, that this is a plugin, so it needs to be abort doesn't really work.
Yeah, and so were you surprised by that? I mean, you probably had the same reaction we did. It's like, well, I guess I understand it in hindsight, but I'm disappointed to learn this.
Yeah, I was definitely. I mean, yeah, the moment I saw the reasoning for it, I'm like, yeah, of course, right? But it was definitely surprising coming into it. Yeah.
Yeah, and then on that, like we have to. I mean, there's not an easy resolution on that, right? We have to basically just change our disposition in our debug builds in order to be able to get, or in our dev builds in order to we need to kind of let the Wookiee win on this one. We can't actually fight with how they want to compile proc macros.
Yeah. So we still ship release builds with panic equals abort set, but debug builds do set unwind now. That's the trade-off, right? I'm fine with it, but one of the reasons we like panic equals abort is that there are cases where invariants can end up breaking with panic equals unwind, and I have a long rant about how standard mutexes are the correct mutex because of this, which I can go into later. But the fact is that we have a divergence between dev and prod now, and we got to live with that.
Yeah, and it's all intention with and what was the what was the win in terms of like not rebuilding all this stuff? Because I think this is the best way to get a win in a system is to avoid doing work completely as opposed to speeding up work, and this avoids a lot of work, right?
Yeah. So the work that I ended up doing to figure this out, like, and kind of put this to bed once and for all, it's hard to give a single number because a lot of it depends on the exact behaviors. But there were like a bunch of cases where so Omicron pull request 4535, which includes this and a whole bunch of other changes that made this work, and like some things that were taking 20 plus second to rebuild now just took 1 second. Overall, for a common scenario with like 4 specific runs, this ended up being a 1.26x speed up, which was pretty sweet. So there's like again, like it depends on a lot of it, and as Sean alluded to, like so much of it is like this. None of this helps with like an individual crate taking a very long time, right? Like this helps when in like other scenarios. So we are still dominated by those long polls, but at least we can improve some of these incremental steps a bit.
Yeah, interesting. And so we talking about proc macros and build scripts. I mean, if people aren't familiar, most people have at least heard of proc macros, and then build scripts are kind of the hard drugs that proc macros lead you to. I found where you could like actually and I have found that you can bloat your compile times very significantly when you get a little bit of a build script problem, which I may have had from time to time. I'm trying to kick it. I'm trying to be clean, but every day is a struggle.
I love build scripts. I mean,
I love build scripts so much. I want to party right now. I gotta tell you, like, let's go on a build script right now. I don't care that I just got out of rehab. I'm ready to roll. I love build scripts, and I kind of feel like the discovery of build. And you know what? Because Cliff showed me build scripts, and he was regretting it as he was doing it, and then immediately regretted it completely. He's like, "Why am I doing that? This is not. You're not going to handle this information responsibly." And I definitely have not. I feel sorry, everybody.
Build scripts, they're just another place where like the handling of inputs and outputs and making sure that you're caching the stuff correctly is just like it's another area where there's a very particular way to make sure that you can do this right. I encountered that like this yesterday actually, where if you have a build script where the dependencies of the build script change, but your build script, let's suppose that it's emitting some artifact, like some output. If that output is exactly the same, even though the dependencies to your build script have changed, everything downstream from that will require recompilation, even though the build script is emitting the exact same artifact. It's avoidable. You can get around this, but like it requires some careful setup to do. And it's definitely not like by default you recompile the world.
Yeah, that's interesting, and it will be it's kind of a surprising result. And so, Sean, I know you've also spent some time just on the performance of proc macros. What were some of the things that you found in terms of what affected build times there? And actually, how did you find that stuff? Because again, I think that's half the trick here or more is like the tooling to actually understand where we're actually spending time.
So for proc macros in particular, this is kind of one of the areas where understanding within a single crate's timing, where time is going, building a proc macro crate, that's something where you can see building that crate itself. You can usually get that information from something like the cargo build -- timings flag. But if you're using proc macros, like let's say that you have a bunch of calls to Cerity, you're using Cerity derive in a bunch of your code. You're using Cerity JSON. You're using a bunch of derives. That's a pretty common thing to do. How much does that cost you? That's sort of information that would come in the form of that single crate build time. So this is kind of a good segue from what we were discussing earlier, where we were talking about like generics and the cost, the binary size of how much that generic costs. But that's, as I mentioned earlier, like that's a proxy for the real signal, which is like, why is it taking so long to build?
Right.
And if you actually want to get information about why is a single crate taking long to build, Cargo actually does provide a self-profiling flag that's pretty decent here. I really want to see more tooling built around this. I personally want to build more tooling around how to interpret this because the feedback is really powerful, but it requires some analysis to make use of it. So the cargo build, I believe it's a Rusty flag that's self-profiling. You can ask for arguments to this thing, and you can basically get out a JSON file that has descriptions in a timeline of like where every single step along the way the compiler was working on things. And if you do this with like the default arguments, it basically gives you the names of a bunch of internal compiler passes, which is not that useful because like seeing, oh, code gem and LLVM passes took up 90% of the time of building this crate is not that informative. Like it's a little informative, but it's not as informative as like which module were you working on? Like what functions were you actually doing work on to produce the thing that you produced? You have to kind of massage this thing to get specific output, but you can get that insight there about like, hey, this is actually what is going on inside the build. Part of the reason that I want better tooling around this is that the output of this thing is a JSON file, and there are some tools built around it, like Summarize is one, and I can give a link in the chat as well to kind of where the family of tooling is around this. But if you have a large crate that's filled with a bunch of stuff that's taking a while to build, you're trying to figure out like where are the slowest spots. You basically are then you need to go take that JSON file and do an analysis on it and figure out like what is optimizable and kind of run your own summations on different submodules and figure out like what are the common patterns. But the next steps there, it's pretty much you're on your own with that JSON file.
Right. You're definitely off road at that point, but I mean, it must be, wild in terms of the amount of information you're getting out of the compiler about what's going where. What did you discover about that? I mean, what in terms of have you been able to go into that and make progress on where time is being spent?
Well, the first thing I discovered on it was that if you ask for the cargo self-profiling to run on a crate like our control, on something like our control plane, and you do it without asking for any arguments, it gives you output that's like in the tens to hundreds of megabytes. But if you ask it to actually profile the arguments and tell me, okay, actually identify when you're working on compiling every type, every function, like write down the function you're working on and when, then it goes up into the gigabytes range of size, and there was a U32 overflow that we bumped into. Which I find this like so poetic, right? Of like, of course, like it's a crate that's emitting a bunch of output. You're doing a bunch of stuff. Isn't that the type of thing that you'd want to be optimizing? Like, I get that if you can have like a simple reproducible case, you can put into like a hello.rs file and just do that. That would be useful if you're trying to like write a repro case for the compiler. But if you're actually trying to analyze a real crate that's very large, like haven't other people bumped into this? But anyway, so that's fixed on Nightly right now, and that will be rolling into the next stable release. So everyone else can look forward to that and not bump into the same problem. But yeah, that's part of why I think more tooling needs to be built here, is because like it is kind of difficult to analyze that file right now. Like I think it contains all the information that one would need, but like you get a very, very narrow slice of what you're actually working on the system. And I think the tools to kind of give you aggregates based on modules and give you aggregates based on functions, especially for the case of like you're deriving something. So the symbols are a lot more specific to where you happen to use that derive. Like if I tried to give you an answer for like, what is the cost of using Serity derive and of deriving serialize and deserialize across all the structs in our crate, I'd love to give an answer for like, roughly this is how much of the total time was spent doing that. But it's not really easy to do right out of the box.
You've got to write tooling that is able to interpret it.
Yeah, which I think is going to be, that's an area where I'm interested in making investments over the next few months, and I think that's something where if anyone else is interested that's listening to this that has similar Rust projects where they want to get better insight there, I would point you all toward that direction because I think there's a lot of low-hanging fruit here. Because this tool is really, really powerful for getting that good analysis on a large crate, but it needs more support.
Well, and I think it's fair to say that more and more people are going to run into these kinds of issues. I mean, there's going to be more and more demand for this kind of tooling as, because I think that, I mean, obviously there are organizations that have had Rust in production longer than we have here at Oxide, but like for a lot of things, we're kind of like relatively close to I mean, just as your U32 overflow indicates. So it's like, it's a good indicator that you're towards the leading edge of something. It's like, okay, I am, but I think a lot more are coming as we there's so many advantages for software in the large for this. It's just this feels like something that a lot of other people are gonna want to hit, are going to hit, and are going to want to get resolved.
Sean, as you were describing some of the things you were hitting with SerDes, it really sort of took the bloom off the rose a little bit for me. Like I view SerDes as this unassailable marvel. But then as you started to explain some of the extreme use of generics and what the code actually turns into, it did sort of make me look at it in a different light. And so I'd love to hear more about like your analysis of SerDes and then also some of the other crates you kicked over as potential alternatives.
Yeah, so I definitely looked into a few of them. I don't really think we've pulled the trigger on any of them yet, but it sort of has opened my eyes to, I get it. I get it now why a lot of these alternatives exist. Like I didn't really understand why like SerDes seems like great if you can use it. It's so flexible. Like why would you need something like mini SerDes? It seems like it's just less useful, right? Or like maybe you have some environment where like you really, really care about a really limited set of things, but like why would I care about something like that if SerDes is working for me? You sort of have to kind of accept that there is like a trade-off that you're making there for generality versus having code that is not generic, that fits a specific use case that doesn't cause increased code generation, and that can act over more generic objects. Like it's just going to take less time to compile.
Yeah, it's like, yeah, sure. All of our API objects could be serialized into CBOR or something, but we don't. Like we always serialize into JSON. So there's a bunch of genericism that we frankly don't need.
So I also want to I think part of maybe what you're experiencing, Adam, too, is this like the back and forth between these things. Like think back to your old C using self and be like, add a couple lines of code and you get a fully fledged, super fast parser for your custom struct with no work.
Totally magic.
Now that's like normal. And so we're starting to deal with some of the downsides of how those things are implemented. But like those are only because everything was so wonderful. But at Rust 1.0, proc macros weren't in the language. Like one of the largest uses of Nightly was people using compiler plugins, which is the predecessor to proc macros, because these use cases were good enough, but like also because they were built around compiler internals, they broke constantly. And it was a huge pain in the butt, but they were like so valuable that people suffered all this different kinds of pain to end up actually using them. And then like Rust 1.15 was like a really, really big important release. Because it was like the thing that stabilized Derive, if I remember that correctly. It's been many years by now, but like that was a huge day. And like right after that, like Nightly usage dropped significantly because people could actually move on to stable for these kinds of use cases. And so I think there's like a natural back and forth, right? Where you get new functionality and then it becomes the new normal. And you're like, why do I got to pay all these downsides for this thing? But it's also worth remembering that like before this world, we also had downsides. And in many ways they were, worse.
Oh,
Steve,
absolutely.
are you telling us that we're ready for the truth that there are no zero cost abstractions? That was a lie that I had to tell you in order to.
So it's funny because even Bjarne and the like C++ people have been trying to use zero overhead abstractions more recently, and by more recently I mean I think like the last 10 years or so. But the meme was so strong that like nobody changes that because everything has a cost. It's true. So it's like. It's about where that cost is allocated.
And I think that like on balance, I also feel that for so many of these things, it's that the pain points are going to only happen at scale, and I think that Rust is so much better on so many of these things than other languages and environments. So I think it's almost I don't know, reassuring, Adam, in a strange way that you're disappointed by. You're just learning the truth. Your parents
Totally
are
fair. I think
your parents
that's
are
right.
fallible.
I think it's just that I found so much unequivocal beauty in Certi. I mean, as you're saying, Steve, and then to find that there was a perhaps hidden cost. I don't know. It's just surprising. Not that it takes any of the beauty away, but just makes you think. In some circumstances, it's not going to be the right tool, and there are reasons for there are trade-offs for the application. There are places where I'd want MIDI Certi, or I'd want some other kind of library.
Yeah, when Sean is kind of what you were saying too about it, kind of like the giving you a perspective on generics versus traits, and like these things become like, all right, these are different tools in the toolboxes at different times, and I may want one or the other for different reasons.
Yeah, and I think I'm coming here being a little bit critical of things like, well, what about all those cases where you're deriving things? What about cases where you're generating code? What about cases where you're generic? Like, and part of the reason that I'm critical here is because I have that mindset on of like, I'm analyzing code, I'm trying to find things that are potentially offenders that cause the compiler to spend a lot of time churning here. But like, I do want to back up a second and say I love Certi. It's a great tool, right? Like it's very, very useful. And like I've reached for it and I will continue reaching for it in the future as well. It's just, yeah, totally understanding that these things have costs.
When how can we just reduce these costs as much as we can? I mean, not, sorry, Rain. I think you're trying to get in there.
Oh, I was just going to say that, I really love Certi. My biggest concern just tends to be that, we have kind of Certi as the ecosystem has committed to this whole, like, it's like a commitment that has been made. It's like the whole, like, pretty much every Rust crate supports Certi in some fashion or the other. And so we have, all of this baked in. So we have gone down this monomorphization path. If we want to switch to something like Mini-Certi, which actually uses DIN, like trait objects using DIN and stuff, then all of a sudden we have to kind of redo all of this work across the ecosystem. And the commitment is like, that's the thing that, kind of just chew on me a bit.
Yeah, interesting.
Yeah.
And then, Sean, you also discovered that link times. So we generate large static executables here with Rust, and that puts new pressure on the linker. Do you want to talk about some of the stuff you found there?
Yeah, so this was an interesting case where we've actually bumped into issues that are actually kind of more platform specific. So we've been talking a lot about like build speed, right? We're talking about different build configurations, which kind of is all lumped into the category of like you walk up to a machine and you run cargo build. But that's only been part of the picture for us internally at Oxide. And like the thing that we really are trying to track at the end of the day is like, what is that developer velocity experience, which is more than just building, right? It's how long does it take to build your code? How long does it take to package it up and put it onto a target machine and deploy that machine and get a control plane up and running and get the whole system running and boot VMs and then ship things onto GitHub and get your PRs merged and move on with your life, right? And the whole process here, and there's a lot of different phases to this. So this is one of those areas where we definitely noticed a distinction between folks that were developing on some platforms versus others. And this is one of those cases where, admittedly, I think a lot of the credit goes to a handful of other folks that did more of this investigation. I know Rye did a lot of this. I know Dan Cross, who I think is here today in the audience, also did quite a bit of time analysis here as well. But this is one of those cases where we, for a certain number of crates that are operating on a very, very large number of files. I mean, we have our control plane. It is split into multiple crates, but at the end of the day, there is one binary that is being built that's linking together all of these different artifacts from different crates. On certain operating systems, we would notice the build time would tank at the end. It would be a bottleneck of like many minutes to actually finish building this binary. And that is sort of the thing where if you definitely would hit this on any single character change, right? You'd have to go through this process of many minutes to rebuild this binary. And that was just very painful for developers going through that experience. So yeah, I can jump into more detail on sort of what we found out within that linker if you want, but
yeah, which in terms of like, so and kind of what our experiences have been with mold and mold being an alternative linker. If
Yeah,
necessary.
so to Cargo's and Rusty's credit, it's actually fairly straightforward to swap what linker you want to use. Like this was something where we had like the theory of maybe the link time is slow and this is an area that we can improve, and we could get like pretty good times to compare LD versus LLD versus mold on different operating systems. There's a small asterisk in there of on certain systems that actually took a little bit of extra work to get mold to actually build. But it wasn't too bad. Like a couple patches we could get there. And in particular on that case, if you're building a lot of crates, each individual one, it doesn't make much of a difference. But if you're talking about that situation where you are assembling a binary that itself is composed of many crates that has pulling all of these large pieces together, you're running one large service that is the amalgamation of many other pieces. We saw a huge difference there. LLD versus LD, we saw a significant jump, and mold was basically the best option across all systems that we saw. Like the time there was quite drastic. It's many minutes worth of difference for the objects that we're building.
And Rain, you've been a long time mold user. Mold is new to me. Adam, I don't know how mold fluent you are.
Yeah, I'm a mold novice as well.
But Rain, you mentioned you integrated into your dev flow a long time ago.
Yeah, I think I saw a link on like Hacker News or something, and I was excited to try it out. Mold is like I love how easy mold is to integrate into Rust. Like it's so smooth. There's two separate ways to do it. Each one of them has upsides and downsides, and so I started using it for my personal builds and stuff like 3 or 4 years ago. It's never had a bug. Well, actually, no. There was one case where it started crashing, but then I had to. Then I think the author released a hotfix. But in general, it's been like a super smooth process, and I've been getting everyone who's is willing to listen. I've been trying to get them onto mold.
Well, I think we got some pretty good. I mean, the numbers are really pretty astonishingly good. I mean, it makes definitely use of multiple cores, and
Dan said in the chat that mold is 400 times faster than Illumos LD for building Omicron.
Yes, it is quite a bit faster on.
On Linux, I remember like I was building a single large service similar to Omicron. It was like 20 to 25x faster on a 12-core CPU.
Yeah, and it will be faster on the more cores you got, the more upside you have there. Because I mean, historically the system linker has been single threaded because it's not something that. For a bunch of reasons, I think there was a lot of movement away from static linking towards dynamic linking, and a lot of time and energy spent on making dynamic linking, making that perform really well. And that's when disk space was at a premium, and there were a bunch of other reasons why we kind of were thrust towards memory was more at a premium. I don't know when that started kicking back exactly, but whether that was where you get these much larger, maybe it was with Go, much larger statically linked binaries. And I think also people were just kind of sick of the dependency hell that you had with shared objects. Certainly ones that weren't versioned well. I mean, there were a bunch of challenges with the shared objects, and kind of the pendulum swung back. And it's like actually static linking is really, really important.
I think,
Stan saying in the chat, it's like you got these kind of, a full featured system linker. It does really great stuff, but it's actually for this problem at hand, it's like actually we want to just like link really, really fast, and we actually need to do that by using multiple cores.
Yeah, I agree, and I think with Rust, like monomorphization basically forces you, for the most part, into static linking because you essentially are copying around object code, right? You don't have a single copy; you have lots of copies of a different function and so on. So this kind of ties back into the monomorphization thing, right? I think those things are pretty closely related.
It also has very interesting implications for the GPL. If you start processing through, this is like a very deep hole with lots of implications that have been built over a very long time that are starting to like unravel in ways now.
In terms of the linking exception with the GPL, or
what Rain was just talking about, like if you're using a generic in Rust, the library has the sort of template, to use a very overloaded word in this context, like saved, and then when you link it against your code, you're like then writing code. Like linkers are compilers. Like the whole separation of these two things is like completely history at this point, and not due to their like actual abilities. Like link time optimization. Like linkers are optimizing compilers in a certain sense. But like it's very unclear, at least to me, and I'm sure there's somebody who maybe in the chat will know of a big giant thing that's written about this, but like when you're basically like running code at link time and inserting that into a different binary, like if I use a Rust crate that's GPL'd, is that going to make my project GPL'd? Is like there's a lot of, it's sort of all built around the C compilation model, and things that don't do that gets a little weird.
Well, I think it's in part because of that ambiguity that in crate like in the crate ecosystem, it is MIT and Apache, right? And you don't see a lot of GPL. You see LGPL, but you don't.
I think that's the kids
for that reason.
I include the kids as being millennials in this point. I think there's been a industry-wide rejection of the GPL, and Rust is just like part of that. Unfortunately, sort of. Maybe ? I don't know. I have really complicated feelings about this topic. It's be a whole different episode.
Yeah, I would say not, unfortunately. So we can have that. Yeah, we'll have to have the debate. We can do the Lincoln Douglas debate, GPL v MIT.
Brian, did you see there? With regard to proc macros, did you see David Tolnay's proposal to compile proc macros into WASM, and then just execute the WASM to generate code? Have you been plugged into this at all?
No. Where do I? Yeah.
I'll put it in the show notes. I'm going to give the simpletons version of the history here, and then I'll let Steve and Sean and Rain clean it up. But I think the simple version is I think David has wanted something like this for a very long time, and got so frustrated in about June or July, August, sometime during the summer last year, that he sort of surreptitiously built a mechanism, or not surreptitiously, makes it sound nefarious, but he built a mechanism into Serde Derive that included some pre-compiled binaries. And then after a few releases, or maybe immediately, opinions differ, some folks sniffed this out and weren't that into it. The fact that there were some binary blobs that were executing in these environments. So there was a big kerfuffle. I think this kind of change that had been around for a little while was reverted, but then David wrote a great kind of proto RFC, which again, I'll link in the notes. But Steve Klabnik, how'd I do? Is that within kind of 50% of accurate?
Yeah, I think you did a pretty good job. I think it's difficult because a lot of this depends on opinions about what happened. And so I think you did a good job of neutrally describing it when it's very easy to non-neutrally describe it.
Maybe too neutral. What is it then?
Yeah, but the short of it is, there would be a bunch of changes to cargo and to crates.io and so on and so forth. But the result would be you're not compiling the proc macro, and as Rain was alluding to, you're not recompiling it, and depending on a sundry of different flags and whatever, you're just executing this WASM. And you'd also just opt into it. Like if you want to recompile it, go for it. If you want to use this WASM binary blob. And then a bunch of other benefits. Talk about build.rs. It's kind of crazy, Brian, that if you think about if you include a random crates.io dependency, that it could run, a build.rs or proc macro code that could do literally anything on your system.
Yes.
Right? It could
it is amazing.
A bunch of secret files and open a network socket and vomit them to it. Pretty astounding. So part of the benefit here would be able to run this stuff in a sandboxed environment.
Yeah, interesting. I could definitely see the appeal. My concern with this kind of stuff is always like, kind of, what if it gets stale or goes wrong, or how do you
totally?
But I also I'm so impressed generally with the robustness of the tooling in the Rust ecosystem. There isn't a lot of that. I guess Sean's issues aside, the U32 overflows aside, but generally the tooling is awfully robust, and we don't have issues with because you always get worried about this object was not rebuilt when it should have been. To me, it's always much more frightening than we unnecessarily recompile this object when we didn't have to. But maybe that's just my disposition towards correctness. If I have to choose between correctness and performance, I still want correctness. But I don't think there'd have been a lot of problems with that, with Rust not recompiling things or being too aggressive with respect to optimizations. So, Sean, what's the kind of the future here? You mentioned getting excited about some of the tooling, some of the profiling, and how you can, making use of that to write now that you've got these kind of bugs fixed in the compiler, being able to build tooling on top of that. I mean, what's the kind of the future for the workflow and dev flow for Rust?
I don't know if this is accurate. I'm going to describe how it feels. It feels like a lot of the tooling that exists around single crate profiling with Rust is built for people who are contributing to Rust C and who want to understand how to make the compiler faster, which I think that's a great disposition, and it's good that those folks have useful tools. I want the future of this tooling to be, here is your crate that you built, and this is where we spent time building this to be in an easily digestible format that you can, as a author of a crate, understand where each different piece in each module, you can understand where derives are taking place, you can understand the overhead of generics, and that's easy to do, kind of navigating through your crate at a module by module level. I think that'd be very, very powerful to have.
Right. You want to be able to answer the question, what's taking so long? And
Exactly.
being able to, and I think also to date, done a pretty good job of allowing people to opt into asking that question, because I think there are going to be a lot of Rust developers as we talked about at the top, compile time doesn't matter until it does. And, when you're first coming into Rust, you may be like, I'm not sure I see what all the hubbub is about. Like, this thing compiles pretty quickly. And, the next thing you know, it no longer compiles as quickly because you've really gone to town on it, and you want to be able to allow people to easily answer that question and be able to, and Steve, I know you've been playing around with Buck too. I mean, do you view that as how important is that to the performance of build times? Where are you on that?
So I know this is purely because we have talked about it a lot of times, but Rain is far more qualified to talk about this topic than I am. I am but a simple baby starting to play with this thing, and I'm excited about it. But yeah, I would actually redirect that question ever so slightly.
Sure.
Rain,
Okay.
Buck too.
Yeah. All right. So I think putting things like Buck 2 in context, I think what Adam mentioned about shipping WASM for a proc macro or whatever. Like, I think that is a special case of a kind of generic approach to caching, and specifically distributed caching, right? So let's say that we are in a world with fully reproducible builds, right? So all your inputs, and that the output for a particular input for a particular step in the unit graph is exactly the same, right? So I think that a lot of the wins, at scale, end up being thanks to distributed caching, where you have these caches that are kept warm by, say, CI machines and stuff, and then local developers can just pull those artifacts down, and the build system does that automatically. So Buck 2 is kind of what I'd like to think of as a totalizing version of that, where what it does is that so Buck 2 is a build system. It's a polyglot build system built out by Meta. It is the successor to Buck 1. Buck 1 was written in Java. Buck 2 is written in Rust. Buck is most closely similar to Bazel, if folks have heard of it. Buck, the way Buck and Bazel and stuff work is that they actually require what they call hermetic builds. So all your inputs must be specified in build files. So you can't depend on anything in the environment. You can't depend on a system compiler. You can't depend on any of those things. And in return, you get the ability to do distributed caching, which is absolutely crucial when you're building services that are at Google or Meta scale. I think Buck 2 is great for what it is. And I think that, in many ways, I can see a future where we do switch to it. I think there are some hurdles that we need to actually look at. So I think one of them is that, as I mentioned earlier, Buck 2 is totalizing, which means that everything, all your dependencies, everything must be expressed in Buck's language so that Buck understands what's going on. That is the only way Buck can work at all. And there is a lot of good tooling built for this. My former coworker, Jeremy Fitzharding, built out a tool called Reindeer, which converts cargo.toml files into Buck nodes. It's pretty great.
Wow.
So for the most part, that works. You have to like manually patch things up here and there, but it generally works. I think the other thing that you have to look out for is that we have a lot of tooling that assumes cargo, mostly out of path dependence. So, there's no particular reason it needs to be tied to cargo, but, we would have to port all of that tooling to using Buck. And an example of that is, in Omicron, we use a test runner called Cargo Next Test. It's a test runner that I'm the primary author of. At the moment, it depends and it's tied pretty intimately to cargo. That isn't inherently the case. We could spend like 3 months making it work against Buck 2. It would be fine. But that's an investment that we would need to make.
Yeah, I do love you calling Buck 1. It's kind of like the World War I, World War II distinction. I mean, did they call that the Great Buck before there was Buck 2? And that's really interesting about the kind of the automated tool, because I do find that like I completely understand why these things have their own DSLs, but then the DSL really makes it that just steepens the ramp to get onto these things. And
I was going to make a joke earlier, actually, much earlier in the episode, about how with your love of build scripts, I'm surprised I have not introduced you to Starlark yet. Because in some ways, so Starlark is the DSL, as you said, but it's actually like a subset of Python that both Buck and Basil use to write
gotcha.
the script part of the build scripts.
So I got to tell you, the thing that I love about the build scripts is that it's in Rust. That's what is like, I just love. I actually don't love Python. Sorry, Python.
I don't love Python. I don't love Python either. There is a small discussion on the Buck issue tracker about writing Buck scripts in Rust, but I don't think that's the thing that's going to happen realistically anytime soon.
So I will tell you that, like, and I came, there have been a handful of times in my career when I thought I was actually going to start crying. And one of them was at the hands of SCONs, what do we say? Which I feel is like one of the predecessors to these systems. Maybe that's an inaccurate read of the lineage of build systems. What's that?
It is not an inaccurate read.
It's not an inaccurate read. Okay. And a part of the problem there was that the language is loose, and that you are, you are having to modify the kind of the scripts of the build system, and there's very little guidance about the flow of execution, and there are no types, and it's just like there's nothing that to really, and I was trying to do was just weird enough, and it was just really, I always feel like it's when you feel that you're like, I'm very close to getting this working, and then that goes on for like 13 straight hours. You're like, I'm now actually like, I'm wearing, tears are welling up. I have been convinced that I'm like 10 minutes away from getting this to work for 13 hours, and I think I'm going to start weeping. And then there was an even weirder one, WAF. Do you remember WAF, Steve?
I don't think I ever used it, but I do know that it exists.
It was Node used it. I mean, like build systems that we have discarded, we humanity have discarded. I mean, that's a grim graveyard of build systems no longer used. But I think
to like provide a tiny amount of color on like why you originally asked me this question and then I pivoted it to Rain is like, basically as part of all this work we've been talking about today, and the fact that we've, one of the first things I did at Oxide meaningfully was like work on the build system for Hubris. And I was like, and then Omicron sort of kind of has a build system in it too. And I was like, we already have 2 bespoke build systems, and this company's like 30 people. And so I was like, I'm gonna write the next standard, like let's just go back and implement a good build system in Rust. And I did all my research and I was like, wow, these are the papers that I want, and I really like the work of these authors. And then I discovered Buck 2, and I was like, oh my God, Meta paid the people that wrote those papers to implement them, and it's already in Rust even, so never mind. And so I have not used it on meaningful projects yet, which is why with Allrain's experience, I went like deflected the question there. But that's like how I got into this, was doing all that research and seeing all those bodies and like looking at what I thought was the best current like theoretical setup for all of this. And but have not really used them in production in anger, let's say, yet.
And so, Rain, this is a very interesting paper. So this is build systems a la carte.
Yes.
Tell me a bit about this paper.
So I believe that this is the paper that Steve was alluding to. Is that right?
It is definitely one of the critical papers that I'm referring.
Yes.
Like I started converting the code in it to Rust code actively one day.
Yeah. So this paper actually it's really interesting because it's written by these. It's kind of this overlap between academics and industry. And one of the authors is Simon Peyton Jones.
Right. Exactly. So we know where this is going.
So what they did is that they actually ended up looking at build systems as used at various places, like something like GNU Make, which is an early example of a build system. Sorry, Make fans. There's and then it also looks at Bazel, Buck, and so on, and finally in a really, I think, inspired choice, it actually looks at Excel, because Excel is also a build system in the sense that it has a whole execution graph of here are the cells that depend on these other cells.
You mean Excel, the spreadsheet? I'm like, this must be a different Excel. You actually mean the spreadsheet?
Yes, yes. And
Adam just passed out. I think Adam.
I'm so excited right now.
So I think, like, actually the folks at Microsoft Research have been really interested in Microsoft Excel because, in a sense, it is the world's most commonly used programming language, and it is like orders of magnitude more popular than anything that any of us in industry use. And so they ended up looking at Excel as well through this same lens, and they found that you could actually break it up. You could categorize all these build systems in a whole bunch of ways. So they look at 4 prototypical build systems: Make, Excel, Shake, and Bazel. And they look at like what kind of scheduler these build systems have. Another crucial distinction is whether dependencies in these are static or dynamic. In other words, can nodes in the action graph create more nodes within them so that can a step produce more steps? And it also looks at things like whether you can share like distributed caching. So they call that the cloud column. So if you look at page 6, then there's a really nice chart showing that. So I thought that this is kind of. I think that this is a really good way to look at it, because it also suggests places where various build systems fall short, or the trade-offs that build systems makes. And I think one of the big trade-offs in practice does end up being the static versus dynamic dependency distinction, because who here is a fan of monads? Because what is so some build systems are don't let you create these additional dependencies, and some build systems do. And the build systems that do in academic circles are actually called monadic build systems, because they behave like a monad, because monad is essentially the ability for each individual thing to create more things of that kind. And so I think just looking at it through that lens makes a lot of sense. And Buck 2 is really principally designed in a very principled fashion, where it tries to make sure that it can use cloud caches and so on, and it tries to use static dependencies as much as possible, but it also has an escape hatch for dynamic dependencies and so on. So it's pretty neat. I think this paper is basically very directly inspired Buck 2. By the ability to categorize the properties of a build system in all these ways.
Now, Rain, tell me if this is accurate, but it may bring it full circle. I was asking David Tolnay about Buck 2 and how it deals with features. And he just said, we don't.
Exactly.
We just pick the features, the end.
Yes. And that is one of those places where, in an open source environment, actually those features, the ability to specify features like in Cargo is very, very useful. But Buck 2 is so designed for the megacorp, we all agree on a shared set of libraries and features. And so, Buck 2 just does not have support for features, and that will be a blocker for us to use it, or we have to think very hard about what we need out of Buck.
What does that mean? Buck 2 does not support features.
So the way Buck 2 works is that right now, we use features. So these are cargo features, right? So these are optional flags that turn on or off various parts of the code base, right? Like single crate, you can say CFG feature equals 30, right? As an example, and then that pulls in that lets you pull in the 30 crate. You can turn it off if you don't need the 30 feature, and so on. And Bazel as well as Buck and Buck 2 don't actually let you say those sorts of things. So you have to say up front, I need the 30 feature or I don't need the 30 feature. And now it's actually great because at that point you don't actually the whole workspace hack thing becomes not an issue at all, right? So in that sense, it is a real advantage.
Yeah. I mean, no need to unify features if you have to if there are no feature support. So yeah,
exactly.
It makes sense.
Exactly. So that's the but that is one of those trade-offs that Buck has a very opinionated model of how it wants the world to be.
Yeah, that's really interesting. And then the flip side of that is that around building at scale and compile times, and then a bunch of other advantages to hermetic builds, of course. So and it's a trade-off. It's a balance, as with all these things.
One funny situation with all of this right now is Buck 2 is actually not hermetic by default, but that's basically a bug. But me and several other people who recently got into it were like, oh, we're so glad that you made this design choice, because I think it makes it much easier as an on-ramp to get started, because you don't need to be fully hermetic. And then you can when you do a remote build, it must actually be fully hermetic. And they were like, yeah, we actually thought that was a bug and we're planning on removing that possibility. And so I still think that's going to happen, but it's kind of as again, an example of that friction and the way you can deal with it or not deal with it in different ways.
Yeah, interesting. And in terms of how you get that on ramp, I do. I think it's definitely interesting to think about these totally different ways of thinking about the build system, and can we possibly move from kind of one to the other? Because it does feel like it's a very big decision and requires a lot of investment. So, as Ryan, as you said, it would not be light for us to move to Buck 2. It need to be a big payoff kind of at the end. We are using Buck 2 for right now. Our current use of Buck 2 anyway, or what will be use of Buck 2 is around FPGA synthesis. So it's looking promising there.
Yeah, and another one that occurred to me is since Rust Analyzer came up, I don't believe that at the moment Rust Analyzer works with Buck 2.
It has gotten way better since. Okay. You hesitated for correct reasons. Specifically, David Barsky has been working on this a lot lately, and I don't believe it is perfect, but it has significantly improved over the last 6 months, let's say.
Okay, that's awesome.
Yes, so. But you're also not wrong in the sense of what you're saying earlier, right? Tools that expect cargo and are used to invoking cargo to do the things they need to do, there needs to be some sort of layer there, and that's complexity.
Yep.
Yeah, well, build times are it's obviously extremely important. It's all around that kind of that developer flow and getting that feedback quickly. And there's Rust gives us so much, and it also gives us the challenge of figuring out how to make our builds faster. So a lot we can go do. This is a terrific discussion. Sean had obviously done terrific work on our own builds, and Rain, all of your terrific work on Hikari and getting that integrated, and then getting to the root cause of this stuff. And Steve, obviously, as you said from the top, like build systems have been something that have been a real important part of your work for a long time. So this is fun. I think that and Adam, Excel is a build system. I mean, you could
Love it. Yeah, didn't have that in the cards, but glad to check off that bingo card.
Exactly. Awesome. Well, this is a great discussion. Thank you, everyone. And I know it's been a relief for everyone to have a discussion in which we didn't mention AI once. So good going. I was tempted to a couple of times. I tell you, I was really very tempted to.
Well, I could go into how Facebook has started to use AI to figure out which builds to run and so on. But
there we go. I knew we were coming here.
Yeah.
I know. I just did it. I just did the thing I said I was going to do. All right. On that note, thanks everybody. Talk to you next time.